Have a nice time to all. Today we will discuss about an algebraic structure called rings. So this particular algebraic structure contains a set R together with two operations, addition and multiplication, between the elements of R. And let me go through the definition of a ring. A ring is an abelian group R plus with an additional composition into from R cross R to R called multiplication. And this operation is named as multiplication. And this operation satisfies the following properties. For every x, y, z belong to R, x into y into z is equal to x into y into z. And there x is an element 1 belong to R such that 1 into x equal to x into 1 equal to x. It treats like the identity element with respect to multiplication. Then x into y plus z is equal to x into y plus x into z. And y plus z into x is equal to y into x plus z into x. So these are the distributive properties. So R plus is an abelian group means that you know all the properties of an abelian group. Addition must be closed in R. Then addition is associative. Since it's abelian, it is commutative also. Then R has an identity element with respect to addition, that is x plus 0 equal to x itself for every x belong to R. And for every x in R, there is an element which is x inverse such that x plus x inverse is equal to the identity element 0. So R together with addition satisfies all these properties, then we call it as an abelian group. And if there is another operation, multiplication also satisfying these three properties also, then we call such an R together with addition and this multiplication as a ring. And some more definitions here. A subset S, subset of R of a ring R is called a subring if S is a subgroup of R plus 1 belong to S and x into y belong to S if x, y belong to S. That is a subset S of R is called a subring if S itself is a subgroup of R plus and the identity element of R belongs to S also, and S is closed under the operation multiplication defined in R. Then we call this subset as a subring of R. And what do you mean by a zero divisor? Zero divisor means you are taking an element x belong to R minus 0. That is, x is an element of R other than 0. Okay. Then if there exists another element y belong to R minus 0, that is y is an element of R different from 0, such that x into y equal to 0 or y into x equal to 0. That means that x and y are non-zero elements of R and you have x into y equal to 0. Then we call x as a zero divisor, or you may call y as a zero divisor. So zero divisors satisfies this property. The product is equal to 0, but neither x nor y equal to 0. And another definition is of a unit. An element x belong to R is called a unit if there x is y belong to R such that x into y equal to y into x equal to the multiplicative identity in R, that's equal to 1. Okay. So x is a unit if it has an inverse. Okay. If this y, in this case we denote this y as x inverse and it's called the inverse of x. So an element in capital R which has an inverse is called a unit in R. R has no condition that a ring has no condition that every element must have the inverse element with respect to multiplication. There is no such condition. And if an x possesses an inverse, such a element in R is called the unit in R. And the set of all units in R is denoted by R star. And another definition, R is commutative if x into y equal to y into x for every x, y belong to R. That is, the ring is called a commutative ring if it is commutative with respect to the operation multiplication. We know that R is a ring, then R plus is a commutative group. So addition is already commutative here. If the multiplication is also commutative, we call such a ring as a commutative ring. Now let me go through some examples. Most natural commutative ring is set of all integers with addition and multiplication. You may check that Z with addition is an abelian group, and also Z satisfies all the three required properties for a ring with respect to multiplication. So thus it's very easy to check in the case of Z. And you may notice that Z star is equal to minus 1, 1. That is, set of all elements in Z which has an inverse are only minus 1 and 1. Because in Z you have to take an integer x and you have to find a y such that x into y is equal to 1. So if you take any x other than minus 1 or 1, suppose I am taking 2, 2 into 1 by 2 is equal to 1 actually, and this 1 by 2 not belong to Z. Okay, so the only units, that is the elements which have inverse in Z are minus 1 and 1. And you know Z is a commutative ring itself, because you know the multiplication is commutative in Z. Okay, so let me go to an example which is a non-commutative ring. So example of a non-commutative ring is provided by the 2 by 2 matrices, set of all matrices of the form A, B, C, D, where the elements belongs to R. Here the addition is usual addition of matrices. You know how to add two matrices, and multiplication also usual multiplication of matrices. You know that matrix multiplication is not commutative. Therefore, this is an example of a non-commutative ring. Another example, the complex number C form a ring containing the integer set as a subring. So C with the usual addition and multiplication of elements of C is a ring, and Z is a subset of C, and Z itself is a ring. So Z is a subring of C. And again, C is a subring of the ring of quaternions. H is equal to set of all elements A plus Bi plus Cj plus Dk, where this A, B, C, D belong to R, where addition is given component wise, and multiplication can be computed by the relations I square equal to J square is equal to K square is equal to Ijk equal to minus 1. So we take the composition table in this way, and the elements here are of the form A plus Bi plus Cj plus Dk. For example, you have an element of the form 1 plus 2i plus 3 by 2 j plus 4k, for example. And this element, when you want to add two elements, say another element in H is 2 plus 3i minus j plus minus 3k. Suppose you can add these two elements component wise, that is 3 plus 5i plus 1 by 2 j plus k. In that way you have to add the elements component wise. That is addition defined here, and multiplication is defined in this way. Suppose you want to multiply these two elements, then actually the elements are multiplying in this way. 1 into 2, that is 2 itself. 1 into 3i, there is no problem for multiplying with 1. And what happens, plus 2i into 2, there is no problem. 2i into 3i, so it is 6i into I, and I into I, it is taken as minus 1. Okay, I square is taken as minus 1, and in that way you can multiply these two elements in H, satisfying this composition table. And this is H together with this addition and multiplication of elements is a ring, and you can treat set of all complex numbers as a subring of H. Some more definitions. The rational and complex numbers are both examples of ring R, satisfying R star is equal to R minus 0. Set of all rational numbers and set of all complex numbers, both are rings. And what about the set of all units in such a ring? Set of all units is all the elements in R except the element 0. Suppose you are taking a rational set of all rational numbers Q, and if you take any rational number, it is of the form x by y, where x and y belong to Z. And talking about the unit, you can say that if an element R belong to Q, R is of the form x into x by y, then the inverse of x by y is y by x. R is not equal to 0, we are considering a non-zero R, this x cannot be 0, so there exists y by x, you can define this y by x, and x by y into y by x becomes 1. So x by y is a unit. So any non-zero element in Q is a unit. Likewise, if you take any complex number, then also you can find the inverse of the complex number. For example, suppose you are taking x plus iy, it's a non-zero complex number, so that x and y both not equal to 0, and the inverse of this element you may take 1 by x plus y. Actually it is the inverse is x minus iy divided by x square plus y square. You can multiply x minus iy to the numerator and denominator, the inverse in this way. So since the element is non-zero, this x square plus y square cannot be equal to 0. So this is defined. So any element in set of all complex numbers except 0 has an inverse. So in both these cases, the set of all units, that is R star is equal to R minus Z0. And a ring R with R star is equal to R minus 0 is called a field. When we see in this example, you see that except 0, every other elements in R has multiplicative inverse. If you have such a ring, such rings are called fields. That is, every element in the ring except 0 has inverse, then we call such a ring as a field. And if K is a subset of L are fields and K is a subring of L, then we call K as a subfield of L. Here if L is a field and K is a subring of L, you can say that this K is a subfield of L. And L is called an extension of K. Another important definition is a domain. A domain is a ring R not equal to Z0 with no 0 divisors. If a ring R has no 0 divisors, we call such a ring as a domain. 0 divisor means that you are taking some x and y in R such that x into y equal to 0, but x not equal to 0 and y not equal to 0. Okay. Such if R satisfies such a property, we call if the element x satisfies such a property, if the x is a y such that x into y equal to 0 but x not equal to 0 and y not equal to 0, we call such an x as a 0 divisor. And if a ring has no such 0 divisors, that means that in the domain you are taking two elements and you see that x into y equal to 0, then you can conclude that either x equal to 0 and y equal to 0. That's the importance of a domain. For example, you can take a set of all integers with addition and multiplication. If you take any two integers m and n, and you are writing m into n is equal to 0, if it happens, you know that either m equal to 0 or n equal to 0. So this set together with addition and multiplication is a domain. Okay. There are rings which are not domains. For example, if you are taking set of all 2 by 2 matrices, for example, you have two matrices. I am writing the matrices in this way. For example, the 2 by 2 matrices 1 0 0 0 and 0 0 1 0 are non-zero matrices. There are non-zero entries in these matrices, and you may see that this product of these matrices equal to 0 0 0 0. So you can conclude that a set of all matrices is not a set of all 2 by 2 matrices with addition and multiplication of matrices is not a domain. So if a ring is a domain, you can conclude that if x into y equal to 0, then either x equal to 0 or y equal to 0. Now let us go through some basic properties about domains and fields. First property is, let R be a domain and a comma x comma y belong to R. If a not equal to 0 and ax equal to ay, then x equal to y. For example, if you are taking set of all integers and we are usually taking if 3x is equal to 3y, then actually we write x equal to y. That is a property here, and we are going to show that this result is true for any domain. Okay, you know that Z is a domain, therefore this property holds there. Likewise, we have to show the results for any domain R. Proof goes in this way. If ax equal to ay, then you can write a into x minus y equal to 0. So since it is a domain and it is given that a is not equal to 0, the property of the domain shows that this one x minus y equal to 0. So and then that gives x equal to y. So in any domain, if you have a not equal to 0 and ax equal to ay, you can just write x equal to y. Another important result is, let f be a field, then f is a domain. That means that every field is a domain. So what do you mean by a field and what do you mean by domain? Field means that every element in the ring has multiplicative inverse. Okay, and domain means that the ring has no 0 divisors. So it is given that f is a field. That means that any non-zero element in f has multiplicative inverse. You have to show that f is a domain. So it is enough to show the extra property that if you are taking x into y equal to 0 in f, if two elements x and y belong to f such that x into y equal to 0, you have to show that either x equal to 0 or y equal to 0. So for that we take two elements x, y belong to f, and we are assuming that x not equal to 0 and x into y equal to 0. Then since we have to show that f is a domain, you have to show that then y equal to 0, because here x into y equal to 0 and x is not equal to 0. So it is enough to show that y equal to 0. The proof goes in this way. Since x not equal to 0, you know that f is a field. Therefore every non-zero element in f has an inverse. So there exists x inverse belong to f such that x inverse into x is equal to 1. And you may write in this way, 0 can be written as x inverse into 0. That may be written as x inverse into xy, because it is xy equal to 0. In the place of 0, I can write x into y. And using the associative property of multiplication, you may write x inverse x into y. X inverse x is equal to 1. So you have 1 into y, that's equal to y. So what you get is y is equal to 0. So we proved that in F, if you take two elements x, y belong to F such that x into y equal to 0 and x not equal to 0, then y must be equal to 0. That means that F has no 0 divisors, or F is a domain. Another example again, consider the subset Q of I equal to set of all A plus Bi such that A, B belong to Q. Actually, this is a subset of set of all complex numbers, because complex number C contains A plus I, B such that A, B belong to R. Okay, so here we are taking only elements A plus Bi such that A, B belong to Q. And we are defining the addition and multiplication of elements of Qi as usual. That is, we are adding the elements component wise and multiplying in this way. And you can easily see that this Q of I is a subring of R with respect to this addition and multiplication of elements. And what about the inverse? If z equal to A plus Bi is a non-zero element of this Q of I, then as we see in the case of set of all complex numbers, you can just take 1 by z. So it is equal to A by A square plus B square minus B by A square plus B square into I. Since this A and B you are taking always belong to Q, this element also belongs to Q. This A by A square plus B square and minus B by A square plus B square also belong to Q. Therefore, this element 1 by Z also belong to, so not Q, it is Q of this. 1 by Z belong to Q of I. And it follows that Q of I is a field, because if you take any non-zero element in Q of I, it has an inverse like this, which belong to Q of I. Therefore, Q of I is a field. And it is an extension of Q and is a subfield of C. Okay, so Q is actually a subset of this Q of I. So you can extend this Q to Q of I. Then Q of I is a subfield of set of all complex numbers. And in complex numbers, you know mod z square is equal to z into z bar. That is, if you take z is equal to A plus IB, z bar is equal to A minus IB, and z into z bar is equal to A plus IB into A minus IB, that is A square plus B square. This is actually mod z square. Mod z is square root of A square plus B square. So this is mod z square is equal to z. Actually, this is a subset of set of all complex numbers, because complex number C contains A plus IB such that A, B belong to R. Okay, so here we are taking only elements A plus Bi such that A, B belong to Q. And we are defining the addition and multiplication of elements of Qi as usual. That is, we are adding the elements component wise and multiplying in this way. And you can easily see that this Q of I is a subring of R with respect to this addition and multiplication of elements. And what about the inverse? If z equal to A plus Bi is a non-zero element of this Q of I, then as we see in the case of set of all complex numbers, you can just take 1 by z. So it is equal to A by A square plus B square minus B by A square plus B square into I. Since this A and B you are taking always belong to Q, this element also belongs to Q. This A by A square plus B square and minus B by A square plus B square also belong to Q. Therefore, this element 1 by Z also belong to, so not Q, it is Q of this. 1 by Z belong to Q of I. And it follows that Q of I is a field, because if you take any non-zero element in Q of I, it has an inverse like this, which belong to Q of I. Therefore, Q of I is a field. And it is an extension of Q and is a subfield of C. Okay, so Q is actually a subset of this Q of I. So you can extend this Q to Q of I. Then Q of I is a subfield of set of all complex numbers. And in complex numbers, you know mod z square is equal to z into z bar. That is, if you take z is equal to A plus IB, z bar is equal to A minus IB, and z into z bar is equal to A plus IB into A minus IB, that is A square plus B square. This is actually mod z square. Mod z is square root of A square plus B square. So this is mod z square is equal to z bar. And we denote this mod z square by norm of z, n of z. Okay, and notice that n of z1 into z2 equal to n of z1 into n of z2. That is, modulus of z1 z2 square is mod z1 square into mod z2 square. And inside Q of I, we have the subring set of I. Set of I means that set of all A plus IB again, but this AB belongs to Z only, not in Q. AB belongs to Z only. So clearly Z of I is a subring of Q of I. And the set of I is called the set of Gaussian integers. Note that n of Z belong to n if Z belong to Z of I. That is, if Z belong to Z of I, then Z is of the form A plus IB, where A and B are integers. And the norm of Z is A square plus B square, and it's always greater than or equal to 0. So then that norm of Z belongs to n. Remember that in this textbook, we are considering set of all natural numbers as set 0, 1, 2, 3, etc. Okay. So if Z belong to Z of I, then norm of Z also always belong to n, set of all natural numbers. Now we will prove an important result. An element Z belong to Z of I is a unit if and only if norm of Z is equal to 1. That means that an element in Z of I has an inverse if and only if its norm is equal to 1. So first of all, let us prove the result. We have to show that the result is if and only if. Okay. So first we are proving the necessary part. If Z is a unit, what happens? We have to show that if Z is a unit, then n of Z is equal to 1. If Z is a unit, that means that Z has an inverse. So there exists a y belong to Z of I such that Z into y is equal to 1. That is the definition of unit. And Z into y equal to 1 means that 1 is equal to n of Z by, that is norm of 1 is 1 itself. We are taking the norm on both sides of this equation. So norm of 1 is equal to norm of Z by, that's equal to, you know the result, norm of Z by equal to norm of Z into norm of y. So product of these two numbers equal to 1, and this norm of Z and norm of y belong to set of all natural numbers. The only possibilities are norm of Z equal to 1 and norm of y is equal to 1, or norm of Z equal to minus 1 and norm of y is minus 1. So that's not possible because that belongs to set of all natural numbers. Negative numbers are not permitted here. So you can conclude that norm of Z is equal to 1. So if Z is a unit, then we concluded that this norm of Z is equal to 1. Now you have to show the reverse part, that is if norm of a complex number is equal to, not a complex number, if a norm of Z were Z belong to Z of I is 1, then you have to show that that element is a unit. That is, we have to provide an inverse for that set. So we assume that norm of Z is equal to 1. And if you take a Z equal to A plus BI, you have to show that it has an inverse. We have norm of Z is equal to A plus BI into A minus BI, that's equal to A square plus B square. As per our assumption, that's equal to 1, because we are taking norm of Z is equal to 1. We have to show that it has an inverse. Then we are providing an inverse for Z in such a way that Z into y is equal to 1. If you take y as A minus BI, which also belongs to Z of I. Because here we proved that A plus BI into A minus BI is equal to 1. So we take this A minus BI as the inverse of A plus BI, because the product is equal to 1. So we proved that if you take any element Z such that norm of Z is equal to 1, then you can find an inverse for that element. Therefore Z is a unit. So the result is Z belong to Z of I is a unit if and only if norm of Z is equal to 1. So using the result, you can find the units of a ring. For example, suppose you have the ring Z of I, that is set of all A plus BI such that AB belong to Z. So which are the units in Z of I? That is, which are the elements having inverse in Z of I? So easily you can see that if Z belong to Z of I has an inverse, then its norm is equal to 1. So if you take an element Z is equal to A plus BI, its norm is equal to, norm of Z is equal to A square plus B square. And this equal to 1, there is a few possibilities there. Z is equal to 1, minus 1, I or minus I. So you can see that norm of 1 is equal to, 1 means that 1 is equal to 1 plus 0 I. Okay. So it is A square plus B square, that's equal to 1. If you take I, you have I is equal to 0 plus 1 into I. So the norm is equal to square root of 0 square plus 1 square, that's again equal to 1. If you are taking minus I, you have minus I equal to 0 plus minus 1 into I. So the norm is again square root of 0 square plus minus 1 square, that's again 1. Okay, so norm is equal to 1 means that you have to take z is equal to 1 minus 1 I or minus I. So these are the units of set of I. Now let us have a new concept called ideals. An ideal in a ring R is a subgroup I of R plus such that lambda into x belong to I for every lambda belong to R and x belong to I. Suppose you have a ring R and I is a subgroup of this R plus, suppose, and you are taking an element of R, that is lambda, and you are taking an element x belong to I. If the product always belong to I, then you say that I is an ideal. That is, product of an element of R together with I belong to I, then we call I as an ideal. Notice that R itself is an ideal, because you take an element of R, again an element of R, multiply, it belongs to R itself. Therefore, R itself is an ideal of R, and that a given ideal I is the whole ring R if and only if one belong to I. You can consider a subgroup I of R plus, that is a multiplicative element of R, it belongs to I, suppose, and if one belong to I and you are taking an element lambda belong to R, such that you have the result lambda into 1 belongs to I. So that means that any lambda belong to R belong to I also. So I is actually a subgroup of R plus, and every element of R belongs to I also, then you may conclude that I is the whole ring R itself. So the result is I is the whole ring R if and only if one belong to I. And the reverse part is trivial, since I is equal to R, it must contain one belong to I. Okay, and let R1, R2 belongs to R. We are taking n elements of R, and we are considering this particular subset, set of all linear combinations of R1, R2, etc. Rn, where this lambda 1, lambda 2, etc. lambda n belong to R. Then such a set is represented by this symbol, and it is again an ideal in R, and we say that the set is an ideal in R, and this set is generated by the elements R1, R2, etc. Rn. And clearly this is a subring of I. Here actually I is finitely generated by these elements, because these are only finitely many elements which generates this particular ideal. And there may be ideals generated by infinite set also. Suppose capital M is any subset of R, not a finite set, M be any subset of R, and we are considering this finite sums, that is A1 F1 plus A2 F2 plus etc. plus AN Fn, where thus A1 A2 AN belong to R and F1 F2 etc. Fn belong to M, and such of all set of all such linear combinations of F1 F2 etc. Fn generates a particular ideal. So actually this set M is an infinite set, but we are at a time we are taking only finitely many elements in M, and consider a linear combination of such finitely many elements of M, and we are considering set of all such finite sums. Then the set becomes an infinite set, and this is an ideal generated by the elements in capital M, which is an infinite set. So there may be ideals generated by finite sets or by infinite sets. And some trivial results here, you may check that if I and J are ideals in a ring R, then I intersection J and I plus J defined in this way are also ideals. And the product I into J is defined to be the ideal generated by set of all Ij such that I belong to I and J belongs to J. And thus trivial results are left to you as homework. Another important remark here, an ideal in a field F is either set 0, that is ideal generated by 0, or F itself. So we are considering a field. Field means that it is a ring in which every element, every non-zero element has an inverse. So suppose this F has an ideal and let it be not equal to ideal generated by 0. So ideal generated by 0 means that it contains only the 0 element. And I is not equal to the ideal generated by 0. We have to show that this I is equal to F itself. Because if this ideal contains one non-zero element, suppose A belongs to I, which is different from 0, then that A belongs to F also, because I is a subset of this F, and every element in F has an inverse. So this A must have an inverse. So we can find a B belong to F such that B into A is equal to 1. So by condition, by the definition of ideal, A is an element of the ideal, B is again an element of I, but actually it's an element of F. So we are multiplying an element of f with an element in I. So by the definition of the ideal, this b into a must belong to the ideal I, and it's equal to 1. So 1 belong to the ideal I. 1 belong to I means that I is equal to f itself, that we have proved in the previous result. Here 1 belong to the ideal I, which implies that I is equal to f. So if f is a field, then either any ideal in f is either the ideal generated by 0 or the whole field itself. Now another definition, an ideal I in R that can be generated by one element is called a principal ideal. In this case, there exists some D belong to R such that I is generated by with a single element D. So if an ideal in a ring is generated by a single element, it is called the principal ideal. And the domain in which every ideal is a principal ideal is called a principal ideal domain, PID. So principal ideal domain means that a domain in which every ideal is a principal ideal. That is, every ideal is generated by a single element. Here you have an example. The ring Z is a principal ideal domain. That is, every ideal in Z is generated by a single element. You have already studied a result that a subgroup of Z can be written as dZ for D belong to Z. So this shows that every subgroup is a principal ideal. That is, every subgroup is here generated by the element D. So every subgroup is a principal ideal. Since an ideal is in particular is subgroup, this finishes the proof. So any ideal in Z is of the form dZ. For example, if you take D is equal to 2, you have 2Z. That means that the set is, you have 0, 2, 4, etc. to the right, and you have minus 2, minus 4, minus 6, etc. to the left. So this 2Z is an ideal in Z. If you take any element of Z, multiply with an element of 2Z, you will get an element in 2Z. So this is a ideal of Z, and it is principal again because it is generated by a single element 2. And the last result of this session, the ring of Gaussian integers set of I is a principal ideal domain. We are going towards some other important PID, that is Z of I. We have proved that Z is a PID. Now we are going to show that Z of I is a PID. Set of I means that you are considering set of all A plus BI such that A and B belong to Z. So to show that Z of I is a PID, we will take an ideal I in Z of I, and we will show that I is generated by a single element in Z of I. So let I be a non-zero ideal in Z of I. So we are providing a particular element in Z of I, and we will show that element will generate this ideal I. The way we choose that element is here. Choose among the non-zero elements in I an element D equal to A plus BI belong to I such that norm of D equal to A square plus B square is minimal. That is, we are taking I as a non-zero ideal in Z of I. So I contains non-zero elements. We are considering all the non-zero elements in I. The element having n of D equal to A square plus B square is minimal. So among the elements of I, which element has least norm of D, we are taking that element as D. And we will show that I is generated by this particular D. How will you show that this I is generated by this element? You have to take an arbitrary element of I, and you have to show that element Z is equal to a multiple of this D. Now suppose Z belong to I, and we compute in C Z by D. If you compute Z by D, here Z is an element of the ideal I, and D is again an element of I having this property, norm of D is minimal, and you are dividing Z by D, and suppose the answer is Q1 plus Q2I. When you divide a complex number by another complex number, you will get another complex number, but here the peculiarity is that Z and D are elements of Z of I. That is, in Z, if it is A plus I by A and B belong to Z only, in D also. But when you divide Z with D, the answer will be Q1 plus Q2I, where this Q1 and Q2 belongs to Q. There may be some rationale occurs here. So in the complex plane, actually the intersection points here this is 1, 2, 3, etc. Here also 1, 2, 3, etc. And this intersecting points of the lines represents the elements of Z of I, because the elements here, suppose this element is 1 plus 1I, that is 1 plus I. In that way, here second element, this point is actually 2 plus I, Okay, and here this point is 1 plus 2i. So you can see that the intersecting points all belongs to z of I. And suppose you are taking some element z by d here. Z by d is an element, complex number such that in z by d, if it is of the form q1 plus q2i, q1 and q2 belong to q. Not a complex number actually. The condition is that this q1 and q2 belongs to q. So you can represent z by d in this way. It may belong to any of the interior of any of the squares. And the result is that you can choose an element in z of I such that the distance between this z by d and that element in z of I is less than root 2 by 2. Because you may see that the maximum distance between 2 points of z of I is root 2. Because here the distance is 1, here also 1. So this is a square root of 1 square plus 1 square, that is root 2. So the maximum distance between two elements in z of I is root 2. And here this element z by d belongs to this, it belongs to the interior of this square. So this is at most a distance of root 2 by 2. In the least case, it may belongs to the midpoint of this line. Then it is the distance is root 2 by 2 exactly. Otherwise, it is less than root 2 by 2. So a point in the complex plane is at most root 2 by 2 away from a point with integer, real and imaginary parts. Therefore, you may choose an element q is equal to c plus di belong to z of I such that modulus of z by d minus q whole square less than 1. That is, distance between this z by d and this particular q is less than 1. Or using the norm, you may write this as norm of z by d minus q is less than 1, because norm of the element means that modulus of the element square. So you can choose an element in z of I such that the distance between z of d and q is less than 1, or norm of z by d minus 1 is less than 1. And we multiply both sides with norm of d, you will get norm of d into norm of z by d minus q, that is norm of z minus qd, which is less than norm of d. So what is the condition for d? We choose d belong to I such that its norm is minimal. Among all the elements of I, d has the least norm. So here we found an element z minus qd which have norm less than d. And we know that this z minus qd belong to I, because z belong to I and d also belong to I. And this q is an element in z of I. So it's an ideal q into d belong to I. So for z minus qd belong to I. So this element z minus qd belong to I and its norm is less than norm of d. So it's possible only if the z is equal to qd. This is a 0 element. So we must have z is equal to qd, and we constructed this element d in such a way that an arbitrary element z belong to I is of the form z is equal to q into d, where q is an element of z of I. Thus, if you take any element in I, it's a multiple of d. That means that I is a subset of the ideal generated by d. And the reverse part, it is very simple. Since d belong to I, we have this one is a subset of I also. Then we proved that I is equal to the ideal generated by d. So I is a principal ideal. So we proved that every ideal in Z of I is generated by a single element. Therefore, Z of I is a principal ideal domain.